but as I said, you should do your search in an organized way and not like, going number by number, because that might not give you any good results. All right, let's see something else. So in part 231, we talked in general about the proofs of universal statements. So if you have proof, to make a proof of universal statement, then you actually need to provide the proof for arbitrary object. So let me see, 2.3.1, universal statement. So in that case, let me consider one example. For all integers n, for all even integers n, or for every even integer n minus 6 over 2 is also even. So what? It's a question here that is this statement true or not? So generally we have two options, either to prove or disprove. If we were to prove it, then we need to start from an arbitrary number. So you cannot just say, let n be 8 or n, because it says for all even integers. That's why this is universal statements, proofs of universal statements. Generally you need to start, so prove, if you want to prove it, then you want to prove it for an arbitrary by fixed, arbitrary but fixed number, even number. So generally we need to start with the assumption that our number, so let n be even. And then what does that mean? That n equals 2k. And from there I want to show that the number n minus 6 over 2 is even. Let me try it. I go 2k minus 6 over 2, because that's n minus 6 over 2. And that is, with a little algebra, factor out 2 and cancel, you get k minus 3. Now I'm a little bit worried. Why? Because there's nothing that tells me that this number is even, because there's nothing forcing this to be even. So now I say, maybe this statement is not true. So what then? So if you get stuck, what can happen? If it will happen that just we didn't come up with a good idea, or maybe the statement is really not true. So generally what I will do, I will test it and try to find a counterexample, so-called. Try to find counterexamples. Find just one. So you see, to prove it, you need to prove it for all. To disprove it, you just need to find one counterexample. And for example, let me do n equals 8. What do I get? n minus 6 over 2 equals 8 minus 6 over 2, which is 1, not even. So what is it? We actually disproved this statement and showed that from the fact that n is even, we cannot prove that n minus 6 over 2 is even. Here's your counterexample. So not true. So generally, once again, you either need to prove it for arbitrary number, and we'll do a couple of those where that works. Here we actually showed it with a counterexample. Here's another example, again, for a universal statement. Example 237. It says the difference of an odd integer and an even integer is an odd integer. Proof. By the way, it's also a good exercise here to record this formally. That's basically what we'll discuss mostly in 2.1. So you see, when you are trying to formalize a statement, here is one of the most important things. To introduce variables. As I said, we don't have to write formal version, but I think it's a good exercise. So this statement is about two numbers, because of an odd integer is one of them, and an even integer is the other one. So we introduce a variable for each of them. So x will be variable for the odd one. Y will be the variable for the even one. So what then? The difference of an odd integer and an even integer. So we say the following. For every x and for every y. So we are just making the statement for any two objects. It's all in integers. So now what? What do we know about x? It says we know that x is not arbitrary, x is the odd one, so we say O of x. What else do we know? We know that y is even, so we know even of y. And then what? We want to prove that their difference is odd. This is what we really said here. So what we said here and what we said here is exactly the same. Be careful, I already mentioned that in section 1, but it's never too much to say that. You have to be very careful about parentheses here, because since I have completely outside parentheses, what it says is whatever x and y, if this true, this will be true. Just for a moment, let me change this and make this one here. Just by placing parentheses there, then what am I saying? This statement stands on its own. And that statement is false on its own. Why? Because what this one says is that for every two integers, one of them is, first one has to be odd, and the second one has to be even, which is not true. If I choose x to be 6, this is false. False follows everything. This is true always. That's not what it says. It doesn't say that this assumption is always true, but it says whenever this is true, this has to follow. So be careful. That's really, graphically it looks almost the same thing, but meaning-wise it's completely different. Anyway, how do we prove that? We say the following. For every x, and so pick arbitrary x. And pick arbitrary y. And then what do we assume about them? We assume that it's not really arbitrary. We know that it's O of x is assume O of x and assume E of y. Okay, so those are our assumptions. And then what? The only thing is, we want to get that x minus y is odd. And actually, I always like here in these settings to talk about crossing the river. So here are the statements. So here is left side, here is the right side, this is the verbal end. And here is the formula end. And you want to go from left side to right side here. This is your verbal statement. So what do? And formal has a bridge, and that's your knowledge of mathematics and formulas. So what you do, you go verbal into formulas. That's what we learned today. Then you cross the river in the formula land, and then you go back from formulas to verbal statement. So that's what we did here. So here it is. O of x is verbal. Now I'll cross to formulas and I say, what does it mean? That means that x equals 2k plus 1. Now I'm in formulas. So this is now formula land. Formula land. Even of y says y equals 2l. It's also in formula land. Look now, I have equations that I can manipulate much better and safer than the sentences. Of course, I didn't say here for some k and z, and for some l. All right, so generally, now the question is, we are among the formulas, how do we cross, knowing what x and y are equal, to what is x minus y equal, because that's what the story is about on the right side. And then what? Just using formulas, it's very easy. X minus 1 is 2k plus 1 minus 2l. And exactly, this is the moment where I cross the river. So this is the story about x minus y in the formula land. But now is the question, can I cross back into verbal land? So can I from this formula somehow conclude that x minus 1 is odd? It should be fairly simple. Those two, if you factor out 2, k minus l plus 1. Now let's call k minus l, let me call it s, which is also integer, because difference of two integers is integers. So this looks like 2s plus 1. So what did just happen? That actually we wrote x minus 1 in the form 2s plus 1, and we have the witness to say, oh, so x minus y is odd. Why? Because of the definition of odd numbers. This is the moment where we crossed from the formula land into verbal land. And that's how it always goes. From verbal to formula, manipulate formulas using your knowledge of algebra, and then back to verbal. And it's good maybe to be aware of this diagram so that you follow your procedure all the time. So that's the proof. Since we did it for arbitrary x and y, we have a full formal proof. All right. And then let me talk a little bit. One of the examples here is about showing that the square of odd number is odd number, works the same way, so I think now it would make more sense. Also, division in the cases. So what would that be? Well, let's do one of the examples. Again, I'll talk about it. Division into cases. So I'll do example and then I'll formalize the principle, and that is example 2, 3, 11. It says the square of any odd integer has the form 8m plus 1 for some integer m. I'll go a little faster here, generally without all these additional writings. But the proof goes the same way. So it says the square of any odd integer. So x, arbitrary odd integer. Now I want this verbal object to transfer into equation. And that is x equals 2k plus 1 for some kz. Alright. Now I want to make conclusions about the square, so that's manipulation using formulas. So now we know that x squared equals 2k plus 1 and then squared. So now I'm trying to cross the river again. So this is formal and this is verbal about x, but now I want statement about x squared. I'm just crossing the river through that. So formal about x, this is formal about x squared. And then I use little algebra, so that's 4k squared plus 4k plus 1. Alright, I look what I need on the right side just to guide me. So that plus 1 I like, I have it, I keep it. But I'm not sure why would this be equal to 8 times something. I can factor out 4, but I need 2 more. So it says k squared plus k plus 1. So basically I need somehow to show that this number is even. So if I can factor another 2. But that's not so obvious as a minute ago, but here it is. I do 2 cases, and I need to prove that no matter which